guys are quite familiar, okay? Like Arrhenius equation in the thermal activity, the process. When we talk about the diffusion, so now we talk about the diffusion in solids, but first, the second Fick's law, you guys has been dealt with in many other chemical engineering classes. So I want to go very fast, okay? So the reason why we care about the thermal process, especially when we talk about the metal, semiconductors, this kind of in the solid state, okay? The difference here in this class, in material science, we talk about the solid state, okay? That's usually different than what we deal with in the traditional chemical engineering, when we deal with the fluids, when we deal with the vapor phase, the gas phase. Okay? So the reason for that is because the thermal process is so important in the solid state. Give you one example. Okay, so we know that when we talk about the semiconductors, pure silicon, there's almost no use, okay, unless for some kind of a basic stuff, okay. So if you really want to use them for the semiconductor device, you need to dope them. You need to on purposely dope some impurities inside, okay. So by that way, we on demand change the electrical property of the semiconductor, okay. So to do that, one most widely used way is using the diffusion, using the thermal diffusion of those kind of dopant atoms, let them diffuse into the surfaces of the silicon. Okay? So by controlling, see for example, the temperature, the diffusion time, we can control how much of the diffusion length is, or that means how deep of these dopant atoms go into your semiconductors. That's very important, okay? So later on when we talk about the semiconductor device, you will see why that process is important. So that's one example, okay? Talking about the thermal activity, the process, and also the diffusion in the solid. So when we talk about the rate process in solid, or that means the thermal process, or the diffusion process, we know that this kind of energy curves, right? It's widely, you guys should be very familiar with that one. If we think about the over energy of the reactants and the over energy of the products, the difference between these two energies, the over energy, will be the energy either released or be absorbed by the process, right? So tell me about that one. If you see a curve like that, if there's a reaction related to that, is that an exothermal reaction or the endothermal? Exothermal. Okay, so easy to understand. Because the product's energy is the reactant. So thermodynamically, you could think about, okay, so the process might be spontaneous, right? Because product's energy here, reactant there. But indeed, as a chemical engineer, we all know that the reaction will also be controlled by the kinetic process, right? So that means the molecule need to gain enough energy to against this activation energy, right? So unless they gain enough energy to above there, and then they can undergo the reaction to release the heat, right? So therefore, the activation energy we need to consider. Okay, very important process here. So, but we know that at a given temperature, not all the atoms have energy above here, right? So that means not all the energy, very small amount in many cases, very small amount to have the energy above the activation energy, then they can undergo the reaction. They can undergo downhill in the energy. So therefore, we know that the probability of finding atoms or clusters of atoms or molecules, that's related to the energy difference, right? That means the activation energy and the energy of the atoms is given by this relationship. And that happens in the Boltzmann's process, right? So therefore, the K in this equation is a Boltzmann's constant. T is at the temperature, the absolute temperature in Kelvin. So that gives you the probability of an atom that has an energy above the, you can calculate at any energy E stage what the probability here, right? So if you draw the distribution of the atoms in different energy, you will see for the atoms or the molecules with energy above the activation energy, the percentage is so small, you're really at the tail. Okay, so that means the activation energy will be dominating in many cases. And also, as I mentioned, if we want to draw, to get a formula to relate the number of atoms or molecules that have an energy over the total number of the atoms, we can correlate that one by using this. So that means we can calculate the ratios of the atoms, the number of atoms, over the overall atom number that has energy above the E star, right? Or at the E star here, on the activation energy. So the correlation constant here, C, is a constant. Okay? So that correlates these two terms together. Don't forget K is the Boltzmann's constant and T is absolute temperature. And also we know that, right? As a chemical engineer, we know the Arrhenius equation, which is relate to the rate of the reaction to the Q. Q is the heat, right? The reaction heat. And over RT. R here is the molar gas constant. You should know the number. T Kelvin. Q is activation energy in joule per mole. C is a rate constant, right? So that's you guys, many of you guys are seniors, so you should learn this one in many classes already. And also we know that the rate of the reaction kinetically, right? In the kinetic class, that depends on how many molecules or atoms that have energy above the E star, right? So, and one common format to show the Arrhenius equation is take the log of the rate, and it's related to the log C, and also the activation energy over RT. If you convert that one to the base 10, then you have a correction term 2.303, right? In this case, we can correlate this one as a linear. You know about that one, right? That's a linear equation, and we know that the y-intercepts, from that you can get the rate constant C from the y-intercepts, and the slope of the curve, is the Q, the negative Q over 2.303 times R. R is a molar gas constant. So by that way, when we plot the log of the reaction rate versus 1 over T, you should be able to see a straight line. And then from the straight line, we should get the rate constant C, or we get the activation energy Q from the curve, right? So that's a quite straightforward way. So one example, actually, we can use Arrhenius equation to study the thermal activation process. One calculation, though I do not have time to do that one in class, but you can see the example in the textbook after class. That is related to the vacancy formation process, okay? That's chapter 4, I already tell you about that one. The energy of formation for vacancies is usually about 1 E-wave, okay? So by that means, if we think about that 1 E-wave is activation energy, okay? So by that means, if you know Q at a certain temperature, if you know the rate constant C, that one usually you can get from the different handbook. Then we can get say for example, or actually we should go to this equation. Okay, if we know E wave, which is 1 E wave, K we know, T we know, C we can get, then we can calculate the number density of the vacancies, right? So that's a process I want you to practice later on. And also, if we think about the atom diffusion process in the solid, we know that the vacancies are very common, 1 out of 10,000 also. And also there's a lot of other crystal defects there, right? Ring boundaries, line defects, and could also have the void there. So, and also, some of the atoms, they should have higher energy enough, their energy enough for them to against the activation energy. So they were diffused. So the diffusion, could occur even at room temperature. Okay. One way to do, I'm going to show you that. One way is the atom will preferentially move to the vacancies because there's no atom there, so atom will go there preferentially. And also, once the temperature is high, usually there's more atoms could leave their original size, generate more vacancies, and then the vacancies actually can transport. So I will tell you about that one later. So usually high temperature, you generate more defects, diffusion will occur easily, right? And so diffusion rate is usually higher at high temperature. And here is some of the processes I'm going to tell you about the diffusion process in the solid state. One is called the substitutional diffusion. That happens usually when there's a vacancy there, then the nearby atom, if they have enough energy, don't forget, when we talk about the energy of this kind of a self-diffusion process, there's two parts, right? One part is you need to have some energy to generate a vacancy nearby the self-diffused atom. So there's activation energy to form a vacancy, plus the energy of the neighboring atom need to have enough thermal energy to let them move toward the vacancy. So therefore, two parts that will add up together to generate the activation energy for the self-diffusion. And usually, when we talk about the metals, when they have a higher melting point, so for those, you need to have a higher activation energy. You need to understand, because chapter 2 we talk about when the metals have a higher melting point, that usually indicate the lattice energy is high. So that means this term and also this term will be high, especially the first one. Okay, if you want to move one atom to generate a vacancy, you need to break this kind of the bonds, the metal bonds in between the neighboring atoms. That will usually, when the melting temperature is higher, you need to provide a higher energy there, right? So, and also diffusion could occur through those kind of interstitial sites, right? Also easy to understand. So the atoms actually can move through, if you think about the blue atoms as the original one, and then when you have a smaller, say for example, carbon. Later on when we talk about the carbonization process, it happens this way, okay? Carbon atoms, say for example, if we want them to diffuse into iron, we know about that. Well, iron is big, iron atom is big, carbon is small, so they were diffused through the iron layers, by hopping through this kind of interstitial sites, okay? So some examples like here, okay? So the carbon can diffuse through the BCC, FCC, gamma or alpha or gamma irons through this kind of the interstitial diffusion process. Chemical engineer, we know about that, right? So when we talk about the steady state diffusion, so that means at any plant, at a constant time, the concentration of the atoms are, is a constant. So by that way, when we talk about that one, we know that the diffusion rate is related to the concentration gradient, right? So that means the difference between that at the higher concentration, though the diffusion is not always one way, okay? Though it's one way, but that does not mean the atom will only move one way, okay? They will move all the different directions, but the net flux will follow one direction, right? So that's a steady state, so you guys should know about that very well. And also we know for this kind of steady state diffusion process, the flux is directionally related to the dc over dx, which is the concentration gradient, and the constant coefficient d, which defines the diffusivity, right? So diffusivity, so give you one example, when we talk about the carbon in the gamma iron at 500 degrees Celsius, and the order is 10 to the order negative 15. This is really a small number, actually. If you compare it to some of the diffusivity you guys learned in the later process, okay? So in the solid process, diffusivity much smaller, easy to understand. But when you increase the temperature to 1,000 degrees, the diffusivity increases by nearly 4 orders of magnitude. So that means diffusivity will be significantly accelerated when you increase the temperature of the process, right? So, and also it's commonly to know diffusivity depends on first is the type of diffusion, right? Either they are interstitial or the substitutional. Interstitial process usually faster when the solvent and the solute atoms are very different size. So, and also temperature plays a very important. Usually diffusivity increase, right, when the temperature increase. And also the crystal structure of the metal matrix also important. Very easy to understand. If we think about the BCC, body-centered cubic, and FCC structure, we know that the BCC structure, the particle occupies the space by 68%, FCC 74%. So that means BCC structure has more open structure, atoms will be more easily to go through them. So therefore, usually, when you have a BCC structure, the diffusivity will be higher than the FCC structure. And also the crystal defects, when we talk about you have more grain boundaries, when the grains become smaller, usually you will see a larger diffusivity there, okay? And also the diffusion solvent, or the solute atoms, where the concentration of them will also affect the diffusion rate, because that will affect the concentration gradient, right? When you have a larger gradient, you will see a larger diffusion rate. Okay, so all these one you guys learned already. Next class, I will very briefly talk about the non-steady state process.